All right, everybody. It's time for percent yield. Percent yield. Oh, percent yield is actually really easy. So, to understand percent yield, though, you need to understand a couple of other smaller concepts. One smaller concept is that, um, let's see, that when you are talking about like limiting reactants and you calculate, so you go from your limiting reactant makes a certain amount of it makes a certain amount of product. Okay. And you could have excess other reactants going on right here adding to this, but the only thing that really matters is a limiting reactant because that will determine how much product you can actually make. So you make that certain amount of product. At least that's what you think. In reality, it doesn't turn out that way. Tons of other factors come in to play. Maybe the temperature wasn't right. Maybe the pressure wasn't right. Maybe chemistry is just a sloppy science in general that is hard to predict, where it's hard to predict what reactions are going to take place because, in a sense, it's a very chaotic and sloppy system. But we like to pretend that everything is going to react. But sometimes it doesn't. For whatever reason, maybe it doesn't have the right activation energy. I don't know, but sometimes it doesn't create as much product you're going to make. Sometimes it's like as simple as, I don't know, dropping something on the floor. Or not getting all of the grams that you thought you were going to get into the container, into the reaction vessel, and to produce your product. Whatever the reason, you don't produce the same amount of product that you think you're going to produce. So we have a way of measuring that difference there, or that percentage that you get correct. And it's called a percent yield. So the percent yield is very simple. It is the actual product that you get in your experiment after you've run it. The actual yield. The yield is the product. Okay? The actual yield, or the actual product, I'll put that in parentheses up above. The actual product over something we call the theoretical yield. Or the theoretical product. All right, so this up here, when we've been calculating how much product we're going to make, that is actually our theoretical product. In theory, yes, that's what should have happened. But in reality, in actuality, it didn't really happen. So the way you report this is you take this, whatever it is, number in grams, divided by this number in grams, and then you multiply that sucker by 100. So, for example, a really simple example right now, let's just pretend that you do all the calculations and, you're supposed to get 9.0 grams. But instead, you get something like 4.5 grams. Oh my God. What happened there? I don't know. So to show your percent yield, you just take 4.50 divided by 9.00 times 100, and oh my God, that's 50%. Make sure that you keep your significant figures along the way here. That's 50 with a 0 at the end. That is your percent yield. Okay? So these problems really are just building on the other problems that we've been doing before. So let's go through a warm-up problem, a simple warm-up problem. At least it should be simple. I haven't taken a look at this yet. So we'll see. Okay, first balance this and then determine the amount. Well, this looks familiar. This equation we've used before. So there's one C right here, there's one C right over there, there's 4 H's, and there's just 2 H's, so I'm going to multiply that by 2, which makes there's 2 oxygen plus another 2 oxygen over there, that's 4. So we multiply this by 2 and everything is gravy. Okay. Which means everything's good. That's the balanced equation, 1, 2, 1, 2. And there should have been an arrow here. My bad. I hope that you realize that. Okay, it says you start with 4.1 grams of O2 in excess CH4. What is the theoretical yield of CO2? Excess means it's extra. So this is, they're telling you in the problem, this is your limiting reactant. This right here is your limiting reactant. So you don't have to bother with going through and comparing how much CH4 would make a product. You don't need to worry about that. And it also shows you that you should be aiming to turn this reactant into that product. How do you know that it's that you're supposed to change this grams of O2 and to see how much CO2 you can make? Well, it tells you right here. It says, what is the theoretical yield of CO2? It doesn't say what's the theoretical yield of H2O. It says CO2. So that means you can look ahead and you can say, okay, since I'm starting with this, I've got to change that into CO2. And I want to see how much CO2 I can make. And they don't tell you in the problem like this, but what they really want you to give that to them in the units, that is grams. They want to tell you want to give this in units of grams here. So let's do it. Very simple here. We take 14.1 grams. This should all be review of O2. And we multiply it by something. What do we multiply by? We multiply it by a conversion factor here. There's going to be something on the top, something on the bottom. We want to change this into moles of O2, so I'm going to have moles of O2 on the top, 1 mole of O2, and then grams of O2 down below. You don't need to have the O2 if you don't want to. It's not that big of a deal. But how many grams of O2 is there in 1 mole of O2? Well, we can figure that out with ptable.com. Pow! Right there, we've got 15.999 grams for every 1 mole of oxygen. So with O2, it's 15.999 times 2, which is 31.998. Some of these numbers, it might help to memorize. Sometimes I find it helpful to memorize these. So this is 15.998 down below. I'm sorry, 31.998. 31.998 grams. But we're not going to stop there with a conversion, so let's continue to make another conversion factor. So we want to change this into CO2. So that means that there are 2 moles of O2 for every 1 mole of CO2. But we're not there, we're not done yet, because we're not going to have our final units be in moles of CO2. We're going to have our final unit be grams of CO2. So how do we change those moles of CO2 into grams? You know how to do this. You put a molar mass of CO2, the molar mass of CO2 up there. What's the molar mass of CO2? I can hear you yelling. It's got to be 12.011 plus 2 times 15.999. If you do that, you're going to get 44.009. So let's put it into this equation here. 44.009. Okay? Now all this is putting in numbers into your calculator. Sometimes people have troubles with that, so be careful here. I'm going to walk through it right now. I'm narrating my steps as I'm plugging into the calculator. I'm taking 14.1. I'm dividing it by 31.998. I'm going to hit enter, because I don't want to deal with parentheses right now. Okay. Now I'm going to divide by 2. I'm going to hit enter. Now I'm going to multiply by 44.009. And I get, I'm not kidding here, I get 9.696 grams. Let's see how many sig figs. You only need 3 sig figs, so this is going to be 9.70 grams. How did I know we only needed 3 sig figs? Oh, right here, there's only 3 sig figs in our starting amount. That's how we know. Okay, that's great. That's a theoretical yield right there. That's a theoretical yield of CO2. So now it says, suppose you conducted this reaction and you had an actual yield of 0.32 grams. That's horrible. Come on. What is your percent yield of CO2? So we know that the percent yield is the actual over the theoretical, theo, times 100. So in this case, our actual, it gives us the actual yield right here, 0.32, and then down below, 9.70. How did I know that? Oh, that's the answer up here. So it's grams, the grams will cancel out, times 100, and we'll be left with our units in percentage. So let's try this. 3.32 divided by 9.70. That's going to give us, oh yeah, times 100. Don't forget the times 100. Times 100. 3. And this is going to be how many sig figs? 2 sig figs right there. 2. That's it. 3.3. That's what I have to round to. Percent. That's our percent yield of CO2. That's horrible. 3.3%. We want something in the 90s. So this person, something went really wrong with their reaction, if that's what they got. But that's the answer. That's the answer to this problem. So that's absolutely correct. Now, sometimes there's tricky problems here where they give you the percentage, and they want you to tell the answer, I guess, in terms of the actual yield. Okay, I didn't explain that very well. So in other words, they say, okay, let's just imagine here that they say, okay, your percent yield really was 97%. Yay! So tell me what the actual yield was. What's the actual yield? So this is a different type of problem right here. So I'm just kind of adding that on here. This is not in this problem. I'm just asking a harder question so you can do it later on. So if you have 97% as your percent yield, and you have this as your theoretical yield, you should be able to tell me what the actual is, because it's using this equation right here. So if you're given this, and you're given this, you can solve for the actual. It's just a simple rearrangement with algebra. Do you want to know how to do that? Let's do it real quick. So this is just another example right here. This is not part of this equation, or part of this question, I'm sorry. This is just an example over here. So I'm going to rearrange this very quickly. I'm going to say, okay, so that the percent yield would be, so if this was, okay, percent yield divided by 100, okay, that will equal the actual over the theoretical, also Walcott. Then we multiply this whole thing by theo, so it's going to be percent yield divided by 100 times theo will equal our actual yield. So if we plug all these numbers in, that would be 9.70 grams. And then we have on top, we have 97% divided by 100. So what would that be? 0.97 times, whoops. 9.409. 9.409 with 2 sig figs, that would be 9.4 grams. So that would be our answer. If we had 97%, our actual yield would have been 9.4 grams. And that should make sense to you because it's very close to 9.7. Anyway, I hope that helps. Ciao.